see me? Okay, so look up here now. Thinking back to your question that your group got yesterday, I want you to,
What we did yesterday.
number one, tell me one part that you're having difficulty with, or maybe that's challenging you. And number two, what's one thing about this question or answering this question that's going well? Okay?
We have to draw. We have to answer this.
I'll give you guys a couple minutes to write that down, and then we're going to share and give me a little bit of idea of how you guys are feeling. Okay, guys, I'd like to hear from a couple different tables. So I know you might have each had different ideas of what was more difficult, but I think you probably have some similar responses since you were working as a group. So would anyone like to start by sharing what they were thinking about as being maybe challenging or difficult? Okay, so let's go to Kevin and then we'll come back to you, David.
Finding evidence, like in the...
Okay, finding evidence.
Yeah.
Who else was feeling like finding evidence or examples to support your ideas? Okay, sort of. All right, David.
Ours was when we were like answering the environment, we didn't know which one, like the label, which one wave, vibration. We didn't know how to draw the vibration.
Okay. What do you guys think about that? Is there any solutions that you can think of? How to draw the waves versus vibrations? Were you talking about vibrations on the drum versus waves in the air?
We were just kind of like how supposed to draw it.
Yeah, any advice? Well, one thing you could do is you could just put an arrow and label what one is versus the other. Okay. Let's see. Other ideas? Anything else we're having difficulty with? Everything? Be specific. One thing more difficult than another?
Except question number one, yeah. Which was, we have to find how the difference in pitch is created.
Okay, so that's the big question that your side of the classroom is answering. If you think about that, one thing I think I was helping people with how the pitch is different, think back to what you've experienced that had different pitches, that you remember about pitch. What were some of the things we did that had different pitches? Tuning forks, perfect example. That can help you think about, okay, we knew that these were different in pitch, right? Okay, what was the difference? Was this high pitch or low pitch? The big one. This was low, so. Okay, do you remember which one vibrated faster? The shorter or high pitch one. Now, you can transfer that kind of thinking about these tuning forks to, you guys have heard me, or you've maybe tapped on those drums yourself. The smaller one was higher pitch, the larger one was lower pitch. Think about what was going on here with the sound, what might be going on there. That can maybe help you think about that. Plus, if you use this as an example, this could count as evidence from which bucket? Bucket number 1 or 2 were the ones that we did tuning fork stuff with. Bucket number 1 was where we actually talked about vibrating this against paper or the ping pong ball. So you can just use examples or refer back to what you know from those experiences, and that's going to be your evidence. Okay? Anything that's going well? I thought we'd end on a good note. What's going well about the question and answering it? I'm going to say one thing I see going well. I'll let you go first, though.
Oh no, I was just saying first.
Okay.
Sure.
I saw that people were drawing some pretty good diagrams of what they thought were happening. So your diagrams and models of what's happening were starting to look pretty good. Yeah. Josh, did you want to share?
Yeah, everything else went good overall except for just that evidence thing.
Yeah, that's, you that's probably the trickiest part.
Strangle myself.
Okay. Go ahead.
Ours, when we roll with like our group, we kind of like agree what to label and what to draw. We kind of did, you should draw the fish. We
Okay.
kind of agree what we want.
So some agreement there. That's good. Sometimes it's hard to work in groups with different ideas. Okay, would anyone like to share what they wrote down? Something you were having difficulty with or something you found challenging? Brian?
I couldn't relate the Rubens to the drum.
Me too.
Okay. That was hard.
So trying to relate the Rubens tube experience to which drum question did you have? Was yours about pitch or volume? Yours was about
Yeah,
pitch. Okay. Can anybody think about how you might relate that?
I figured it out.
I wasn't here, but I think that since the Rubens tube, the sound waves travel through, and with the drums, the sound, that's when you strike it travels through the drum.
So maybe draw some parallels there.
Yep.
Okay. Jose?
The length of the wavelength. Because if it's short, it means it's high pitch, and if it's long, it's deep pitch.
Deeper. Yeah. Okay. Good. Other things that were difficult? Yeah.
I would say like I don't know, like we couldn't really draw the drum. Like we all tried, and then Muhammad got it.
Okay.
So yeah.
So you worked through it and you found somebody that could draw the stuff on top so people can see it. Yeah. Say it.
What we did for evidence.
Okay. Read it to me.
Evidence. When we did the Rubens cube, the flames were low because the speaker was on low volume. When it was turned up, the flames rose. Also, when we dipped the fork into the water, it splashed a lot. When we hit the fork hard, when we hit it soft, it created less splashes. That's what I thought evidence what you meant.
Okay. Now you're using that to kind of back up your explanation.
Yeah.
Will you share your explanation with me too? So then I can see how that fits to that.
Sounds have different volumes when you hit the drum hard or soft. Is that volume is based on how much force is exerted into the instrument. The harder the hit, the larger pulse is created in the sound wave. When the object is hit softer, the pulse has less force in it to make a soft volume. And then when a drummer hits the drum hard, the vibrations are harder which make a louder noise. Now, if the drummer uses less force, the vibrations are softer. That means a lower sound. In other words, the more energy that you use to hit the drum, the louder the sound. The less energy, the lower the sound would be.
Okay. And then when you were saying that
But the flames.
Dude!
Let me hold on. I was going to go back to this part. Also when
We dipped the
we
fork
dipped the fork into the water, it splashed a lot. Okay. Now, when you're saying it splashed a lot, that's an observation. What do you think that showed?
It showed how much energy it pushes out.
Okay, or I was,
Transferred?
and I was thinking, were you saying that because you're saying that there's
more energy,
there's more
force involved?
I don't know. I was just curious what you were thinking.
Yeah,
So if that would be the only thing I might clarify is just say, after you kind of make a statement, you could tie it back to this and say this shows that.
Oh,
this.
the bond of energy.
Yeah, but otherwise that's really great, Josh.
Like they're flexible, more flexible.
Okay, so you're thinking that relates the same way. The more flexible drum head would be lower. Alright, cool. So let's see. In your explanation of what's happening and kind of your writing, where you tie back into the experiences here, how's that going for you guys? You're already done with that? Okay. So let's see. One of you guys read this for me, because is it your writing?
Yeah.
Handwriting? Yeah, will you read it out?
The sound waves from these two drums are different because the small drum has a higher pitch, which is because the sound waves move faster. The sound waves move faster because they are more contained and have less of the space to move around, but just as many sound waves. This also depends on how hard it's hit. The big drum's pitch is lower because the sound waves don't vibrate as fast because they have more space to echo or bounce around. One piece of evidence we used from the buckets was that the smaller the object, the higher the pitch. Also, smaller objects vibrate faster than larger objects. This means the air particles are moving faster, which causes a higher pitch.
Okay, now I've noticed it sounds like you've almost used two pieces of evidence. One was about the tuning forks, it sounded like different size, different pitches. And then also,
Well, yeah, that's what I said. Also,
okay, so what I would say is you need to try to use some evidence from each of the ones. But right here, how is it that you came to know about the air particles and how they're moving based on these things we did in class? Was it through the reading materials? Was it through the Rubens tube?
the Rubens tube.
Okay, so you could say, comma, we know from whatever it was in the Rubens tube, and tie that into there to strengthen your statement. And then try to figure out how you could use something either, well, the last one could be ideas about slinkies or things that came from the readings. And then the other one that we've got is with tuning forks and GarageBand. Now you guys are doing pitch, so we measured pitch and volume with GarageBand. Was there something in GarageBand that lets you know how pitch works with the instrument?
The tuning and the key. The tuning and the key.
Okay, so using the tuner and knowing the key, what did you notice as you did different things with the tuning fork? How did the pitch react, or the key react to the different things you did?
Well, as like time went on, like after about 7 to 10 seconds, the key would like start to drop down to like D and B from say like a C.
Okay.
So it would drop to B, and then it would drop like all the way down to a B.
Pitches. Okay. Now, have you thought about overall? Do you think that change in key is happening with the strength of the volume, or do you think it's having to do something with the tuning fork actually changing?
It's the strength and volume.
Strength and volume. Okay. That's kind of what I was wondering.
Because when we would hold it up close to the thing, it wouldn't change at all. If we held it right next to the computer, the key would always stay the same.
Okay. So.
But if we had it like hand width away, or the arm length away, it changed really fast. Like it would stay at C for a little while, and then it would start to change right away.
Okay, so I don't know what you think about this, but maybe you could incorporate part of what you learned about the pitch staying the same into thinking about how is the pitch going to be for these drums, as either the sound gets quieter or as someone's standing further away or closer to it. See if you can kind of add something like we've just talked about there. And then I think you would have included something from each one. Okay? So I'm going to move on.
The examples from each bucket, like what do you mean?
So, based on what we did in those different things, first one was using the tuning forks against paper or up against a cup of water. What kind of information did we get from that helps us solve this question? One of the things I can think of is that when we hit the two different tuning forks and then I asked you to do it against paper, that's where we uncovered the idea that the vibration of one is faster than another. So, that's one way you could use that, because the question says, why do the sound waves from these two drums have different pitches? Well, I see we've got those labeled high pitch and low pitch, and I think your experience from band and Melissa's experience from at least playing with those in here says the same thing. The small one's kind of high pitch.
It's gotta be bigger. Yep.
Now, if you think about the vibrations of this, is this one going to be vibrating fast or slow compared to the other size one?
Fast.
Okay, so thinking about it vibrating fast, then think about how the air is acting next to it. We had the tuning fork vibrating against air. We have the drum vibrating right up against air. Then how does that make the energy traveling through the air look different? Remember when we kind of drew out what we thought they looked like in Slinkies? Or investigating pitch and volume?
Oh yeah, that one, okay.
I'm confused. So check this out. This is more of where I was going here. It says how the energy wave causes the difference in pitch. So the difference in one wave, or the way one wave looks compared to another,
Like that's
that affects its sound. So if it's all a bunch of waves
Okay,
crunched
yeah.
together,
I got that one. Is this a big enough drum? Yeah, we'll just label it. It'll work.
so if you were to see, like, you close your eyes and you envisioned like a bunch of little closely spaced compressions, would you say that that's a high pitch or a low pitch? High pitch, right? It's the quick vibrations that cause that. Now, if you were to talk about the wave, you could talk about that difference being the reason for
We're missing one more word. Density.
that difference in sound. And the evidence up there that taught you the most about how waves were spaced, what would you say? Is it
Rubens too.
okay? So you could say because of our experience there, you know, we could see that this was actually happening. All right. All right.
You don't have to relate it.
Here's the thing. You can just, to make this easy, let's focus in on one drum. Because we're really only changing how hard versus soft we're hitting it. Okay? So which drum would you like to focus on? Big one or small one? Okay, so let's look at that one. So if we think about the sound energy coming out from that hit, going into the air, it's vibrating all the little dots of air around it. Okay, now it's vibrating them kind of like this. Some are squeezed together, some are apart. Some are squeezed together, some are apart. Now, this is what's happening when you hit real hard. There's real dense little waves that are compacted. Now, when you hit it less hard, there's some parts of the air that are squeezed together and some parts that aren't. But notice, are they as squeezed together? No. So that's how you would draw the difference in the two, loud versus soft. What I'm envisioning, and I won't really draw this, but can I see this? Is that you're showing, can I make a couple dots? Okay. You're showing some dots here. And you know how we're showing that some are squeezed together? So if you wanted to draw these as the ones that are really squeezed together here, right next to it where they got hit, then the ones next to it could be less. And then you're going to have another area where you have a lot. And then another area where they're not as much. And then so on. And if you think about that going all away from it, that could be like, I heard you say in circles.
We do it like a wave. You know how they do it? It's not a wave.
Like,
I mean, like, you
you're
know how
thinking
you
like
say
this?
Yeah.
Think about it like what you're saying, Kim. It's not a wave like that. It's a wave like this. So, the reason why we used the slinkies was we showed how...
I mean, like, you know how they do like this smoke waves, or you know how they have little... You could do it like that, but like
what I would,
like a design.
Well, what I would like to see is less... I can think of a couple ways you could show it and it'd be really neat looking, but I want you to show it more scientifically. And this would be more scientific than the earlier idea. So not only are you going to have a little strip of sound coming down from the bottom, but this is going everywhere around this drum, right?
I still don't get it.
I'm going to show you one of the diagrams, and I'm not sure if you were here.
I wasn't.
So maybe that's part of it, but see this picture of the tuning fork? Can you see the little dots there? Okay, as this tuning fork hits those little particles of air that are invisible, it hits them, and then they hit into another one, and they hit into another one, and hit into another one. And you know, have you ever watched dominoes? Okay, dominoes fall over. One hits the next, hits the next, hits the next, hits the next. Now if you envision these like dominoes, the dominoes are falling like right here. And it's just this like wave of energy falling from one thing to the next, to the next, to the next. That's what's happening when you hit that drum. You hit it, and those little air particles hit the next ones, and they hit the next ones, and the next ones. I would say, since you're focusing on this drum, around where you're thinking they're traveling on just this one. And then when you want to show the loud versus soft, you make the change like this versus this. So if this is soft, you could draw a little area over here and label it and say this is what the air would look like when we hit the drum hard. I'm gonna leave you to do this. Do you want to leave this here or put it back up there? Okay. And I've also got this drawn on here. No, I don't. Never mind. So.
We're done.
Take care. How about your explanation? So here's your explanation here.
Yeah.
Okay. So let's see. You want to read it out for me? I'll probably. Well, it'll probably be easier for you to read your. It's good, but it's just easier.
If you hit the drum hard, it makes a loud noise because it has a strong vibration. If you hit the drum softly, it has less vibration, so the noise is softer. The more energy you use, the louder the volume is. The harder you hit the tuning fork, the stronger splash there was toward the water. When you hit the tuning fork, it made a noise and we put it toward the computer. GarageBand showed that when the tuning fork was hit hard, the volume was loud. If the tuning fork was hit soft, the volume was more quiet. For the Rubens tube, if the volume was high, the flame was small. Then if the volume was low, the bigger the flame was. If the volume was loud, the slinky was more packed together, and if the volume was quiet, the slinky was spaced out more.
Okay, so I'm really impressed with this. That's a really good way you integrated the evidence into your writing. And that's a hard thing to do. You know, I was gonna ask you something else here for the Rubens tube. Hey, just real quick, you guys, folks that are done, I need you to stay at your tables, okay? You said something about that the flame was small and then the flame was bigger. Now, I know we had changed the volume a little bit. Now, do you remember with this? You said when you turn? You were thinking when I turned up the volume, the flame was.
They said it was smaller.
It was smaller.
I said it was bigger.
When I just turned the volume, the flame flames went up. But I also was doing something else, which was I changed the pitch.
The pitch made it smaller, the volume made it louder. Or bigger for the flame.
I would say this. When I turned the volume down, the flames went down in height.
Yeah.
When I turned it up, the flames went up in height because there was a bunch of air getting pushed on in there, and it was pushing up more. When I changed the pitch, what was happening is the spacing of the high flames was changing. It was low pitch, the high flames were spaced out. High pitch, the flames were spaced together. So talk about that again and see if you need to change anything there. Otherwise, this looks really great, and I'll come back and look at this in a second. Okay? I'm going to come back and look at it in just a second. Like you showed with, I think, and you turn it in, but I can bring it back to you. You know where we talked about how the sound was traveling around the tuning fork? Yeah. I remember you did a really good job at showing where all the sound travels, and then how within that space, how the sound wave is different. Well, what I was thinking as I started saying that is just where all is the sound going, and then within the space, you know, how is it different? Like you've already included these, which I think is good, but you could also put, you know, is there sound in this region versus this region, and
or like where around the drum is more.
Yeah, so you could add that. Now, Luis, you were gone yesterday, and what I was thinking, maybe Brian, you could introduce a little bit of this to Luis, and then also ask him how he's thinking we could either add to this, or if we could change anything here about evidence that you use to support your answer. Okay?
Alright, I like doing that. That's fine.
Okay.
Let me just draw it.
Really short. I bet it was like really quiet. So the farther away it was, the fainter the sound was.
Low pitch? Drums are low pitch. The bigger drum. The bigger drum is gonna go. I'm just saying, look at this. If you hit it harder, it's going to seem like it sounds more rapid.
Okay, well, there's two things that can happen. You've got a certain pattern that happens to the air when there's a loud volume, and then there's a certain thing that happens when it's higher pitch. Now, what is your question asking about? Volume
Do
or
you think that's right?
volume? And when it's hard versus...
The compression, the farther away it is,
Okay, now let's think about this. When you hit a drum
less
hard,
compressed it
is the
is.
drum going to vibrate against the air soft or hard? Hard, right?
And what about the wavelength?
Air hard. That air is going to hit the other air really
And the
hard.
rest position?
It's going to hit into the other air with a lot of force, and so on. Okay?
Yeah.
Now when we
Let's put it in here. Oh,
notice how much the spacing between the compressions, because the spacing here, if those are close, that's a high pitch sound. If the compressions are spread apart, that goes slow, because that has to do with how fast something vibrates. If that's slow, this
Pink packet.
I don't have an extra pink packet, but maybe that group does.
I have a pink bag.
See if you can borrow from him. Hey guys, how you doing?
I filled it out.
You filled it out. Oh, all right.
I used the word. But I didn't understand these two, and I didn't understand these four, like how to put it in a sentence.
Okay, so when we, have you ever heard the word compress?
Yeah.
How are you thinking it's been used? If you compress something, what do you do?
Push something down harder.
Push something down harder, or together?
Yeah.
Okay.
Now, like this.
Well, it could be either direction, like down like that, or down like this. Like you could compress a pillow, make it into a smaller area. Now, when we're talking about compression with sound, what do you think we're compressing? Any ideas? Air. Remember whenever we talked about remember when we talked about hitting against the paper?
Oh yeah.
Think of all the little particles of air out here. When you hit this up against them, it's going to push those air out here. It's going to push that together. Okay? So that's kind of how that word's included in here. So, let's see. I see you've got here a drum that's vibrating, and then you're showing, what are you showing down here?
I didn't draw that.
Air. Yes. Teresa, will you grab your pencil and label that air? Okay, and label this side air too. Okay, now when you think about, is this going to be your loud one, or is this one going to be your loud one?
Loud one.
Okay, so label this loud.
And this soft or quiet?
Okay, yeah, you can put quiet. Okay, so if you're calling this one loud and this one quiet, I see that you've drawn the air a little bit different.
She drew it.
Teresa, what do you think is different
Like
about?
it's just making it slow and this is just making it fast.
Okay, so when we talk about slow versus fast, I think what that goes better with is when we talk about like a high-pitched noise and a low-pitched noise, like versus like those difference. Like when we had a tuning fork that was high, really high-pitched, that moved fast. When we had a tuning fork that was low, like that was moving the air slow. With volume, which is what we're talking about here, when you hit the drum, think about how hard the drum is hitting up against that air.
Hard?
If you hit the drum hard, it's going to hit up against this air hard, right? So watch what happens. If we think of the slinky as air, okay, if I hit the drum slow, or not slow, sorry, lightly, this is maybe what the air is going to look like. Now what if I hit it hard. See what's happening? What do you notice? Well, I was moving. Actually, what I'm trying to show is I'm using less force. I'm going to go the same speed with my hand, but look what happens to the air when I use more force. See how it gets more squished up there? So on the loud one, some of these air, let me see your pencil, Leon. What I would do here is I would draw some of this. See how those are close together? See how the air is close together? That's because it just got hit real hard with the vibration here. Now, on here, it's not so much. See how they're further apart? It's because the drum's not hitting up against the air. So, as this energy goes away, there will be another area where these particles are really squished together. And then here, you may have them kind of pushed together a little bit, but not as much. Sort of, what are you thinking about that so far? Does it seem to make sense how you could compress air with a lot of force? What if you do this? If you move against the air really fast?
I get it now, because like when you hit it soft, it's not barely touching, it's not barely moving. But if you hit it hard, that's when it hits hard, it pushes out faster.
It pushes the...
Like when you go like this, when you go like this, it's barely touching it, but when you slam it hard, it's barely, and it's moving a lot.
Yeah, if you think about it as just the amount of force you're using up against the air, it affects how scrunched together it is. See, when you use less force, now push it real hard. See how that gets more squeezed together? Yeah, and do it real soft. See how if this were sound traveling through air, the air's not getting very squished together, right? But try it with a little more force. That's like a louder drum. So what you might see is there would be areas where the air is really compressed, not so compressed, really compressed, and then what would be next? Not so compressed. Now how would you draw this side? This is the quiet side. Okay, so I'll have you guys go ahead and draw some more, and then I'll come back and see how you're feeling about it, okay? Can I take this? I know. Okay, just giving you guys the 5 minutes.
I think it might get more compressed together.
5 minutes left to work on your stuff. I'm kind of moving around.
Yeah, because if it's even soft, it'll still get together somehow.
How are we doing over here? This drum totally makes my
Yeah, it doesn't have to be. No, stop it. So, can I check in real quick, Casey, with you? Would you mind reading what you got there? Because what I'm thinking is that I'll have approximately you guys on this side, and maybe if you guys can share yours at the end. You guys are doing the one about pitch, and I'm curious which parts you pulled from your experience.
Mine basically is like 4 paragraphs.
Okay. Let's see I think, yeah, or would you mind?
I just couldn't find it.
Okay. So what I wanted to do is have a few people, one maybe group from each side, share what they've got right now. I know there's a couple groups that are still working on their stuff. So what I think we could do is pause for a minute. I think 5 minutes would allow one group to share across and another group on this side to share across what they were thinking. And we'll see where you're at. What I'd like to do is have one person from the group read out your explanation, and then one other person from the group come to the front, and I'll help you show your diagram on the document camera. Okay? Do you guys want to share yours? Actually, you know what I'm going to do? I'm going to have you guys share. I really like the way you used evidence there. And then Marcos, I haven't seen your drawing yet, but let's bring it up anyway, and we'll show it.
I'll go off.
Bring it up, Robert. And Danielle, would you mind reading yours? Okay. No, you can just turn so the class can hear your voice. But wait for just a second before you go. Okay, so just to get us all aware, this is the question that we're going to be doing an explanation for, was how these sounds have different volumes when you hit hard versus soft. Okay? So, let's get the diagram up here. I'll move it around a little bit. Let's go ahead and hear what you wrote first. And you guys, I want you to really listen to this because I think they used evidence within their writing really well and it flows really nicely. So, take it away.
If you hit the drum hard, it makes a loud noise because it has a strong vibration. If you hit the drum softly, it has less vibration, so the noise is softer. The more energy you use, the louder the volume is. The harder you hit the tuning fork, the stronger splash there was toward the water. When you hit the tuning fork, it made a noise when you put it toward the computer. GarageBand showed that when the tuning fork was hit hard, the volume was loud. If the tuning fork was hit soft, the volume was more quiet. For the Rubens tube, if the volume was high, the flame was high. But if the volume was low, the flame was smaller. If the volume was loud, for the Slinky, it was more packed together, and if the volume was quiet, the Slinky was spaced out more.
Okay. So, just take a look at the drawing up here. We've got a drum, right, being hit two different ways. Roberto, which way is this being hit? Is this the loud or is this the loud? This one's the loud. Okay, so let's go with this one. This one being loud, let's see how they show the energy traveling through the air. We have a compression wave with the parts labeled. Now let's look over here. Comparing it to the soft, we have compressions and rarefactions, also a compression wave. What's the difference between this one, the soft one, and the loud one? What are you guys noticing that's different?
Compression, the soft one is smaller.
Okay, so we have different size compressions. Is that what you're showing? Which one has the bigger compressions?
The loud one.
The loud one. All right, good. Okay, so this will be just enough time to, I think, have, let's see, James or Tyler, Jacob, either any of you, would one of you guys bring the drawing of your group up and then one of you will read? So let's do the same way we did before. You guys can read and then we can look at the drawing.
Sound waves for these two drums are different because the small drum has a higher pitch, which is because the sound waves move faster. The sound waves move faster because they are more contained and have less of a space to move around, but just as many sound waves. This also depends on how hard it's hit. The big drum's pitch is lower because the sound waves don't vibrate as fast because they have more space to echo or bounce around. One piece of evidence we used from the buckets was that the smaller the object, the higher the pitch. Also, smaller objects vibrate faster with larger faster than larger objects. This means the air particles are moving faster, which causes a higher pitch. In GarageBand, we experienced differences in pitch due to the distance and time. This would also be true to the drum. Using the Rubens tube, we saw that the higher pitched sound, the more waves there were in the fire. With a low sound, there was one shallow wave.
Okay, so Tyler, would you like to point out a couple things on your drawing to the class and what you're showing?
Alright. For the smaller drum, right, smaller space to vibrate equals higher frequency because
when you hit the drum, I guess it makes a higher sound, but it makes a faster vibration. And the space right here, makes it vibrate because if you hit it hard, it's still gonna be low, but you're not gonna get as much get much faster vibration because it's bigger and more of it will bounce around. I just basically said those ones.
Then you're showing
Oh,
here.
and then right here, the tightness of the drums. If the small one was tighter, it would be a louder sound, louder pitch. And then this one was like not as tight as the higher one. This one would be lower, like really low.
Low pitch. Okay. All right, you guys. Thank you a bunch for those people that shared. I've talked to 2 different groups from 2 different sides. Okay. I'm going to have one group share what they wrote, what their explanation was, and then what their drawing shows. I'm going to have same thing from the other side. You guys on this side were doing volume. This side was doing pitch. Now, what I want us as listeners to do, stop where you're at right now. What things would you want to see in a drawing? Yeah.
The drum.
You'd want to see the instrument. What else are you going to need to see there? Okay?
The sound waves.
The sound waves, Mohammed? You might want to see how it's being sensed.
Yeah.
David?
How air particles shift in the air.
Awesome. Okay, so how air particles go shift in the air?
Yeah.
Okay, so let's look for air particles and how they're representing them. Let's look for how they're showing a wave. And then maybe with the instrument, like how the instrument's doing its thing, okay? So let's watch for those things as we either hear the explanation or as we look at the picture that's being shown, okay? So, would you guys start, Brian? Luis, come on up with the picture and I'll get you started here. And if we can give them our full attention, they will appreciate it, and you guys will get here in the view.
You just messed up my super plate.
Just come up here and set it on.
You smell just Slinkies with these.
Okay, good. Okay, Brian, you can go ahead and read your explanation of what's happening.
Smaller drum is the higher pitch because it is smaller, and like the tuning fork experiment, the smaller it is, the higher the pitch. It's the same reason the bigger drum has a lower pitch. This all has to do with the flexibility of the drum head. In the GarageBand experiment, we saw that the stronger the vibration is, the louder the sound and the more intense the pitch. With this, I can tell that since the drums are different sizes, they can't make the same amount of vibration and they won't have the same pitch. From the Rubens tube, we learned how the pitch moves molecules through the air. So with the drums, the sound waves would be different because the air molecules move differently to cause the pitch change. With the wavelengths are different, it makes it sound. The Slinky experiment told us the difference between how high-pitched and low-pitched sound is. With the drums, because the smaller drum has less flexibility, the wavelengths become shorter, making the compressions more frequent and making a higher pitch. And the bigger drum has more spaced out wavelengths, so lower pitch.
Okay. So let's see, Luis, will you point out which side they were showing as high pitch, or that you guys were showing as high pitch? Sorry. Okay, and then which side was the low pitch? Okay. Now, I noticed that you guys show it both in the way that the energy would travel through a Slinky and through the air.
Yeah. With the Slinky, you can see easier.
Okay. Now, for the class, is there anything? Did they meet our expectations with showing the instrument and what it's doing? They show the air particles.
No.
Yes, they did. It's hard to see because it's light, but they are up there. And they also represented.
They're here, and then they're in the sound wave itself.
Okay.
Yeah. And they also showed a representation of a wave of energy. Anything you'd like to see added? All right, awesome, guys. So, are you guys at a point where you can come up, Alex and Leticia? Or one person read, one person point out? Okay.
Just give it a title.
We'll see if we can get that under here.
I have to zoom in on it.
So I might adjust it for you. Let's show the title first. Volume.
Seems pretty cool.
And then let's do the same sort of thing. Let's we'll listen and watch for the same things: particles, waves, and the instrument, how it's doing its stuff. Right?
Forgot we have to switch off.
Oh, right. Yeah. Good.
The amount of energy determines the volume of the sound. So the harder you hit it, the louder the sound. The density of the waves are more compressed when the drum is hit harder. The harder you hit it, the more vibration you feel. The flames of the Rubens tube represented the air particles of the drum sound wave. The higher flames represented compression, and the lower flames represented the rarefaction of the wave. When the drum is hit harder, more energy gives a higher sound by having the compressions tight and the rarefactions further apart.
As the sound travels away, the sound decreases and the waves spread out. The farther the distance, the less your ears catch the sound wave. When an object creates a soft sound, the compressions are less together. The wavelength is not usually different between soft and loud. The compressions and refraction are different, but the wavelength is about the same. To measure the wavelength each second, it is called frequency.
And yes, sir.
I'll zoom that for you.
The compression and rarefaction of high and low pitch.
Let's zoom this because we can get a pretty good shot of that. You can just move it up and.
When it's higher, the air particles are more compressed than the lower ones. Those are compressed, but not as much. And then these are the wavelengths. They're the same length, just more compression, but higher, more volume.
Okay. I really like how you guys showed that the wavelength stayed the same, because if it changed, what would be changing? Pitch. Yeah. Good. So, have they met what we were looking for? They showed the instrument and how it was doing its, making its sound. I guess that was verbal. We saw the air particle arrangement, and then down in the detail section we saw how they showed waves traveling through the air. Okay. Would there be anything that anybody, or even your group, wish you could add or change? Thank you guys. Both groups are really great. Thank you guys. That's really nice.